Alright guys, so in this video we're going to talk about three things that are very specific to waves. So um, particles, they move through space and they can change velocity, but a particle is always located like in one spot, in one position. That's what makes it a particle. Waves move through space as well, and they have a certain speed, as we saw, and that relates to its wavelength and frequency, but they also can go through each other. So particles, when they collide in space, they bounce off each other, right? Well, waves can go through each other, and they can change speed as they go from what's called a medium, so one medium like air into another medium like glass, right? And they have different speeds, and when that happens, they get bent. So we're going to look at these three phenomena in this video, and we'll talk about it more in the next two classes. And you guys are going to look at, you guys are going to do some activities where you look at these properties of waves. So the first thing that we're going to look at is wave refraction. I'm sure you guys have heard this before, this wave refraction. And refraction occurs when the speed of a wave changes. So in this instance, we have a water wave, and notice that there's a certain distance between the crests of the wave, right? When water is when waves move through deep water, they go at a fairly fast speed, and then when they get into shallower water, they slow down. Okay, there's a drag that gets applied to them, and they slow down. And what happens is they get bent. Okay, so originally it's kind of going in this direction, and after it gets bent, it's going to go more in that direction. So there's this turn that occurs as it goes from deep to shallow water, kind of that way, right? There's a turn away from it, and that is called refraction. Now notice how the wavelength changes. So this distance right here is longer than this distance right here. And that can happen. As waves go from one medium to another, the wavelength can change. Because remember, we have the speed of a wave is going to be equal to its frequency times its wavelength. And the frequency of a wave will be the same. Okay, so that's going to stay the same as it goes from one medium to another. We know this is true because if you look at light, the frequency of light corresponds to its color. And as this green laser beam goes in light, it gets bent, but it's still green, right? So the frequency will stay the same. Well, if the frequency is the same and the speed goes down, then that means that the wavelength has to go down. The wavelength has to get shorter. So the frequency will stay the same. The frequency of a wave stays the same as it goes from one medium to another, but the wavelength can change. Okay, and that's because the speed's changing. So we're going to look at refraction. We're going to look at this bending of a wave in the direction of its travel as it goes from something like air, where light travels quickly, into something like water, where honestly it still goes quickly, but not as quickly as it does in air, and how it gets bent, right? It gets bent. So that's refraction. Now, one of the cooler things that waves do, in my opinion, is that they interfere with each other. And we're going to talk an application of this that came up within the past few years in astronomy. But to understand why it happens, as I said, waves can travel through each other, right? They can occupy the same space at the same time. And so as they overlap, what can happen is they can build up, right? So if a crest overlaps the crest, then you add these two together and you get a bigger amplitude. Okay, so the amplitude will increase. When the amplitude increases, that's called constructive interference, right? So constructive means to build up, right? So they build up, and the resulting wave, the wave that you would actually see, is has a bigger amplitude than the two waves that went into it. But they can also overlap so that you have a crest and a trough overlap with each other. And when that happens, they'll cancel each other out. Now, if they're, if along the whole wave, crests and troughs are overlapping, then the whole thing cancels out. This is destructive interference. And if it's perfect, it's going to be zero amplitude. And this is the basis of a lot of noise canceling headphones. What they do is they take a sound wave, from the sounds around you, and then they will produce their own sound that, it's called out of phase. So they produce the same sounds, but they'll shift it so that the crests of the incoming sound waves now overlap with maybe troughs of the sound waves being produced by the headphones. And when that happens, it cancels out the sound. Okay, and so then you can, I don't know, if you're on an airplane, you can sleep. I see a lot of people using noise canceling headphones on airplanes. So that's the basis, that's the technology that a lot of these noise canceling headphones use, this phenomena of destructive interference. Okay. Oh. I'm not done yet. Oh, I skipped one. Okay, so wave superposition is the last one I wanted. So let me start the slideshow here again, guys. Sorry about this. So let's see current slide. All right, so wave superposition follows from this, right? So not only you can have two waves overlap, and they may not overlap perfectly. You may have, say, maybe this blue wave along here, and you have the green wave along here. Some of the things we notice is that their wavelengths are different, and therefore the frequencies are different, but they can overlap in space at the same time. And so you'll have areas like here where we have constructive interference, and then we'll have areas right here where we have destructive interference. And when they overlap at the same time, the resultant wave is the addition of the two or all the waves that go into it. In fact, musical instruments sound the way they do because any musical instrument produces not just one frequency, but a lot of we're called overtones, so kind of like multiples of that frequency, and they do it with different amplitudes. So a trumpet sounds like a trumpet and not a piano because of all the waves that combine in a trumpet, and all the waves that combine to make a piano sound are a little bit different. So you can play, like, say, a middle C on a trumpet, you can play a middle C on a piano, but you can tell whether a trumpet or piano plays it, even though the frequency, the fundamental frequency, will be the same for both. And so we'll look at that more in class as well. Okay, so these three phenomena, wave refraction, this changing of the speed of a wave, as it goes from one medium to another, one spot to another, causes it to bend. It causes the wavelength to get shorter because of that, because the frequency is the same. We have wave superposition, where we can overlap waves in space, so waves can pass through each other, unlike particles. And when they do that, you add the two waves together, and there'll be some parts that when you add together, they'll interfere destructively and cancel each other out, and there'll be other parts that when you add together, they'll interfere constructively. Okay, and so that's the phenomena of interference. Okay, this constructive and destructive interference, this building up and this canceling out of waves. So as I said, the next two classes, you guys are going to be doing some virtual labs that look at this. Honestly, it's just easier with waves to do virtual labs. We used to use like these ripple tanks, make waves in water, and it's very difficult. So this should be much more clear cut, and you guys should more easily see the phenomena that we are learning about. So as always, if you guys have any questions, please let me know.